The subway system has become one of the most significant elements in the evolution of modern urban transportation. As cities have grown larger and denser, the need to move millions of people quickly, safely, and efficiently has led to the development of underground transit systems that reduce dependence on cars and buses while relieving the surface-level congestion of city streets. Subways represent not just a form of public transportation, but a highly complex engineering achievement that integrates urban planning, mechanical systems, and human-centered design to serve as the backbone of mobility in metropolitan areas. Their role goes far beyond simply moving passengers, as they also influence real estate development, economic activity, and even cultural identity in the cities where they operate. Historical development of subways. The first subways were created in the 19th century to address traffic congestion caused by horse-drawn carriages and early automobiles in growing cities like London, Paris, and New York. London's Metropolitan Railway, opened in 1863, is often recognized as the world's first subway, using steam-powered locomotives that were later replaced by electrified trains. Other cities soon followed, realizing that underground networks provided both an efficient solution to traffic and an opportunity to expand urban areas without gridlock. Subways became symbols of modernization, representing a city's progress and ability to adopt advanced technology. Over the years, subway technology evolved from basic tunneling techniques and steam engines to electric traction, advanced signaling, ventilation systems, and automated ticketing. Today, modern subway systems incorporate digital technologies, real-time passenger information, and increasingly, driverless train operations. The subway system has become one of the most significant elements in the evolution of modern urban transportation. As cities have grown larger and denser, the need to move millions of people quickly, safely, and efficiently has led to the development of underground transit systems that reduce dependence on cars and buses while relieving the surface-level congestion of city streets. Advantages of the subway. One of the main advantages of the subway system is its capacity to transport vast numbers of passengers within short periods, making it one of the most efficient forms of public transportation. Unlike buses or cars, subways do not depend on traffic flow, which means they can operate on a fixed schedule with predictable travel times. This reliability is crucial in large metropolitan regions where millions of commuters rely on punctual service every day. Another advantage is environmental. By reducing the number of cars on the road, subway systems help lower carbon emissions, reduce fuel consumption, and improve air quality in cities. Additionally, subways save space in urban environments by being largely underground, which allows surface areas to be used for walking, green spaces, or commercial activities instead of wide highways. Subways also enhance economic activity by improving access to jobs, schools, and services, leading to higher property values near stations, and stimulating investment in surrounding areas. Disadvantages of the subway. Despite their many benefits, subway systems come with notable disadvantages. The first and most obvious is cost. Constructing subway tunnels, stations, and infrastructure requires billions of dollars in investment, which can put a significant burden on government budgets. Maintenance costs are also extremely high, as underground environments are prone to water leakage, mechanical wear, and structural degradation. Subways can also be disruptive during construction, requiring years of excavation that impact surface traffic, businesses, and neighborhoods. Another disadvantage is vulnerability to overcrowding, especially during rush hours. Finally, security remains a concern as subways are vulnerable to crime and in some cases terrorist attacks, given the large number of passengers and the confined nature of underground spaces. An important physical phenomenon associated with subway systems is the shaking or vibration caused by train movement through tunnels. These vibrations originate from the interaction between wheels and rails, as well as the transmission of energy through the tunnel structure and surrounding soil. Passengers often experience mild shaking during acceleration, deceleration, or when the train passes over joints in the tracks. For nearby buildings, vibrations can also be felt depending on the depth of the tunnel and the type of soil above it. Engineers mitigate these effects by installing vibration-damping pads, floating slab track systems, and resilient fasteners that reduce the transmission of vibrations. While vibrations can never be entirely eliminated, modern subway systems are designed to minimize discomfort for passengers and prevent structural damage to surrounding infrastructure. Successful subway cities. 3 of the most successful cities in terms of subway and urban transportation systems are Tokyo, London, and New York City. Tokyo's subway system is widely regarded as the most efficient and punctual in the world. Trains in Tokyo rarely run late, and when they do, delays are usually measured in seconds rather than minutes. The network integrates seamlessly with above-ground commuter rail systems, allowing millions of passengers to travel across the metropolitan region each day. What makes Tokyo unique is its use of advanced scheduling algorithms, real-time monitoring, and cultural emphasis on punctuality, which ensures that even during peak hours, the system operates with remarkable efficiency. London's Underground, known as the Tube, is historically significant as the world's first subway. Today, it operates across a vast network of lines covering both central and suburban areas. London has invested heavily in upgrading its infrastructure, introducing contactless ticketing through the Oyster card system, and modernizing its trains with air conditioning and digital passenger information systems. The Tube is also an essential part of London's identity, symbolizing the city's history and resilience. New York City's subway system is one of the largest in terms of track length and number of stations. Although it has faced challenges such as aging infrastructure and occasional service delays, it remains the lifeline of the city, carrying more than 5 million passengers on a typical weekday. The system operates 24 hours a day, unlike many other subways worldwide, which makes it indispensable for a city known as the city that never sleeps. Efforts are ongoing to modernize the network with digital signals, accessibility improvements, and more energy-efficient trains. Other uses of subways, shelters, and beyond. Beyond transportation, subway systems have historically been used as shelters during times of war and crisis. During World War II, London's underground stations served as bomb shelters for thousands of civilians during German air raids. Similarly, subway systems in other countries have been repurposed as shelters during conflicts or natural disasters, providing protection against external threats due to their underground location. Technologies for developing subways. The development of subway systems involves a combination of civil engineering, tunneling technologies, mechanical systems, and digital innovations. One of the key technologies is the tunnel boring machine, TBM, which allows engineers to dig precise underground passages while minimizing disruption at the surface. TBMs have evolved to handle different soil types from soft clay to hard rock, and can even operate under water tables without collapsing. Ventilation systems are another crucial technology, ensuring that underground air remains breathable and safe by circulating fresh air and removing pollutants. Signaling technologies have also advanced, with many modern subways adopting communication-based train control, CBTC, which allows trains to run closer together safely, increasing capacity and efficiency. In terms of passenger experience, innovations such as automated ticketing, real-time mobile apps, and platform screen doors have improved both convenience and safety. Finally, the rise of autonomous and driverless trains marks a new era in subway development, reducing operational costs and enhancing precision. Socially, subways provide equitable access to mobility, enabling individuals from different socioeconomic backgrounds to access jobs, education, and cultural opportunities. However, the environmental costs of construction such as energy consumption and habitat disruption during tunneling cannot be ignored. Moreover, subways often drive gentrification in neighborhoods near stations, raising property values and sometimes displacing lower-income residents. Balancing these impacts remains a challenge for urban planners. Future of subway systems. The future of subway systems lies in digital transformation, sustainability, and resilience. Cities are increasingly adopting smart technologies such as real-time monitoring, predictive maintenance, and AI-driven scheduling to optimize operations. Energy-efficient trains powered by renewable electricity are being introduced, reducing reliance on fossil fuels. Moreover, future subway systems are expected to be more resilient to climate change, with flood-resistant tunnels, heat-resistant materials, and advanced emergency response systems. The integration of subways with other modes of transportation, including autonomous vehicles, bicycles, and electric buses, will create a seamless urban mobility ecosystem. Subways will continue to serve as the backbone of urban transportation, adapting to new technologies and societal needs.